Okay, then the last talk for today will be held by Daniel Prades. He have a full professorship here at the TU Braunschweig for distributed sensing since 2024. Before he was in Barcelona, he's founder of a company Color Sensing. I don't know if you will tell something about that. Also.
Yeah.
And he's working there on medical applications also. And today he will give a talk on fluorescence multi-detections with a lensless micro-LED array. Okay, the stage is yours.
Wonderful. Thank you. Thank you for inviting me here to present a bit of what we do in my institute at TU Braunschweig. We work at the Institute of Semiconductor Technology. So we are microchip guys, microchip people, semiconductor activities. It's actually today my anniversary in TU Braunschweig. I make 1 year since I'm here. So yeah, something to celebrate. I'm happy to share a bit with colleagues. I was invited actually to talk a bit about this development. This is the result of a long time collaboration. It was possibly the last project I had in Barcelona. It's in essence a good example of the success we have collaborating in multidisciplinary ways from different institutions. In this case, it was Barcelona and TU Braunschweig mostly. Does it work? That's why. Okay, I will not use it anymore. So that's what we did in the past. It's actually a system, a component, a tool, yeah, that tries to measure fluorescence in a more convenient way than just a top bench system that we may have in the laboratories. And that's in essence what we do. We try to develop new tools which make systems that today work in the lab a bit more compact, a bit more portable, a bit more useful for applications. So the take-home message of my talk, I hope it is, get a look in the possibilities we have in technology, and maybe if it resonates with your research interest, just let's contact back and let's stay in touch to see if we can find new fields of applications. That's actually what I do in the institute. I am in charge a bit of linking microchips with applications. So I really like to visit these places where I learn things about molecular communication and these fancy words that we do not know, and try to be helpful there. Unfortunately, I will be running right after my talk. Yes, so for being in touch, you will see my email there. So feel free to approach anytime, whenever you wish. Before jumping into the description of this tool, I would like to give a bit of a context of the kind of things or the kind of technologies we have here at REACH, at TU Braunschweig, and in the region, more generally in Niedersachsen. Yeah, the first thing is clarifying what nitride is, which is the workhorse of our technology, which is the nitride technology. This is a kind of semiconductor material that we use, and specifically, this is good to operate with light and to put light into smaller and smaller microsystems. In microelectronics, as you know, the big player is silicon for many years, already 70 years. We've been learning how to make it extremely affordable and to process it in extremely complex ways. That is the electronics that we have in our daily life. But the second guy into this fight would be the nitrides in general. These are extremely interesting because silicon has something good, which is that it is cheap and affordable and well controlled, but not especially good at anything. Instead, nitrides are a kind of material which are good at several things, and many things actually, specifically in things related to the interaction with photons, the interaction with light. These are what we call direct bandgap materials, which means that they are good for the interplay between photons and electronics. And if we mix a bit them different compounds with nitrogen, this is why a nitride is, we can cover a broad range of wavelengths from the UV to 100 nanometers down to the infrared. So it's good to play with many different colors if you want to put it in this way. Actually, a good example of how nitrides have been successful is the white illumination with LEDs that we have all around. It was the Nobel Prize in 2014. In this room, yeah, it's still fluorescent, but in general, when we have white LEDs, what we are talking about is gallium nitride, is nitride materials. This was the big boom of this technology already in 2016. And over the years, you will have seen several novelties in the market, for example, 5G, 6G. When we talk about electronics, 5G, 6G, this is possible because of nitrides, because they are fast semiconductors of high mobility in the electrons. They are also good at dealing with high temperatures. So they are quite good also to handle power electronics. So all these fancy small chargers that we have nowadays with the phones are possible, again, because of the nitrides. And it's a kind of technology that is in everyday's life, and we expect in the future to have a big role, especially in several fields that are quite in vogue, like quantum, artificial intelligence, and specifically, or more specifically, sensing. And today it will be a good example of how nitrides could be good for sensing. However, we still need 70 years to catch up with silicon, sort of saying, right? So nitrides are good components for specific functions, but they still cannot provide us with the complexity that silicon is bringing us. So typically what we need to do to take advantage of the advantages of nitrides is combining them with silicon. This means integration, and technically it is called hybrid integration, yeah? Combination of different semiconductor technologies. That's exactly what the Nitride Technology Center is, this little icon up there. This is the branding mark, the branding we use here in Niedersachsen to support the activities in nitrides. The situation is quite clear, right? In Europe, we have an issue with semiconductor industry. We are lagging behind, period. There is a window of opportunity, which is trying to find materials and technologies which are not so much developed worldwide. So nitrides are an option, and their integration with CMOS, it could be potentially a way to be competitive in the long run. This is something that Lower Saxony believes in, and we have quite a focused investment to try to put together the teams in the region, Braunschweig, Hanover, and many other places, so that we can deal with the production of the nitrides themselves, the processing of the microchips, and also their integration with silicon. That's, in essence, the competences that we have here in our university and in the region as well. Before jumping into sensing, a quick word about other potential applications, the fancy word quantum. Yeah, quantum computing, quantum technology, we will see what it means in the future, yeah, but that's true that nitrides could help there. And in this sense, quantum technology at least is the driving force for the development of a set of technologies that later you will see that we can apply also for sensing, but let me just give you a few hints on how they can be applied as well to quantum applications. To begin with a micro-LED arrays that I will show later, the single photon detectors that I will show later in more detail, but also cavities and ion traps that maybe have some connection with some kind of molecular processes that could be carried out in some specific complex experimental setups that you could imagine. First of all, micro-LED arrays. What is a micro-LED array? So it's an array of micro-LEDs, which means that it's not a display. This means that this is a set of LED emitters put together side by side, making a square configuration, a grid configuration, or any other thing. That's the difference between display and array. The whole idea is that we need many different emitters, but we don't need them to show images, but we need them to produce light patterns. And this could be, for example, to excite certain molecular excitation bands, to modify certain materials with the use of light, and so on and so forth. So it's, in essence, a technology that allows us to put light sources extremely small or much bigger, extremely sharp, extremely fast, in an arrangement which is convenient and fit for the purpose of an application, which typically is not looking into it. Yeah? So it's like using light for manipulating things. That's a technology we developed over the years. You will see an example functioning later on. But just to mention CubeDot, this is one of the startups here in the city, established by our institute, and is actually commercializing this kind of designs and technologies. It's quite interesting because it's been the first technology which has gone through the 3 stages of the European Innovation Council here in Europe. So Pathfinder, Transition, and Accelerator. So to our knowledge and to the knowledge of the Commission, here in Braunschweig, we have the honor of having the first one succeeding into these 3 things that I guess points at that this is something kind of interesting from a commercial point of view, at least. Another activity we are into is my colleague Stephanie Kroka. She just received a project to develop what she called integrated resonant cavities. When we talk about lasers and coherent light sources, one typical experimental configuration is defining a cavity which is multiple of the wavelength of the light so that it bounces back and forth, creating interferences, interacting with molecules, you name it. But setting up this kind of thing is a really experimental problem. You need to have a proper optical tabletop bench with things to adjust the length with temperature, to inject light, to extract light, to measure light, and so on and so forth. What we are working on is trying to get rid of all these problems in the laboratory and trying just to have the cavity with 2 microchips, which will be the mirrors with all the control and everything integrated. That's something that it might be of interest for somebody, at least in the future. Other uses of that is quantum computing. Quantum computing, the approach followed here, at least in this part of Europe, is quantum computer based on one strontium atom floating in the middle of a vacuum, and then carrying out interferometry experiments with the optical properties of this atom. Of course, you can imagine that holding one single atom of a strontium in the middle of the vacuum is kind of tricky. And this is one of the bottlenecks of this kind of technology as of now, which is the creation of these chambers with magnetic fields to hold the ion floating there in the vacuum, hitting from several directions with laser beams and so on. What we are trying to do is developing optical microchips where the atoms can be held suspended in the middle. Yeah? The idea is using just one laser source and three different diffractive grids that reflect back the beams. They focus in one point and they hold the atom together with magnetic fields in this position, running the interferometric experiment or whatever is needed. Might this be useful for some other ions interesting for molecular communication or other fields? You are there to tell me. I don't know. But this is just one possibility that we have this kind of fancy molecular control technologies. Before jumping into the topic of fluorescence measurement, which would be the topic for today, let me just show you another example, because I've seen before people showing magnetic beads moving around, tracing the trajectory of a particle here and there. And maybe this is also something that could be interesting for you. That is based on the micro-LED arrays that I was mentioning before. The idea is that we can use our microchips, our micro-LED arrays, to build up what we call distributed microscopes. You will see why it has its name. The working principle of these microscopes is shown up there, and the idea is the following. So if you have a micro-LED array, meaning that you have very little light sources spaced one beside the other, you could switch on and off one after the other. And just imagine, like in this image, that on top of these micro-LED arrays, you have an object. And of course, if the object is covering one LED or not covering one LED, the shadow that it projects on a detector on top will be different, right? If there is an object, you have shadow. If there is no object, you have no shadow, put in simple terms, yeah? So just by blinking the lights one after the other, you could project an image directly on a detector without the need of any magnifying lens or anything like that. What brings you here the ability to see really small structures is the size of the LEDs. You will see, you can imagine that the size of the information you get in terms of spatial distribution is the size of the LEDs. Yeah? I can tell you that we can produce arrays where the pixels are 200 nanometers apart. So this means that we can produce images of this kind of shadows, if you want, with pixel resolution of potentially in this range. Yeah, 200 nanometers, we are already talking close to the super resolution limits. Yeah, so it's pretty interesting. The summary of this thing is that to make it work, you just need the micro-LED array and an optical detector on top, right? So this means that the system can look potentially as something like this. Actually, it looks like that. Yet a couple of microchips making a sandwich and a channel in the middle, something that is small as a coin, if you want. And of course, you can put it around a fluidic channel where you can grow cells, where you can acquire images all the time without any bulky lens or anything like that. Yeah? You can imagine the potential of that. That's why we call it distributed microscopy, because it is potential a microscope that you can produce in large amounts. What we need to build this microscope is a 3D printing housing and a couple of chips, a nitride and a CMOS chip. That's it. So this can be produced in masses, and you can start imagining interesting experiments. Like, for example, if you have fluidic channels, organ on a chip, Petri dishes in an incubator cabinet, you can monitor all of them at the same time. You can have one microscope monitoring all the experiments and keeping them running all the time, taking pictures, taking video, whatever you want. Yeah? So far, what I described are applications based on pure optical transmission images. It's also possible to work in reflection mode, and more interestingly, it's also possible to work in fluorescence mode. So one can get images where the information is not just out of the absorption in the sample, but also from some marked fluorescent dye or whatever you have. Yeah, for example, if one thinks in magnetic beads functionalized with some fluorophore or so on, these kind of things could be tracked, monitoring, if this is interesting for any kind of experiment of relevance in this community. So that's a bit of a long introduction of the kind of things that we have around. And now let's jump into how all these technologies could be combined together to put up a little instrument that could help us to measure fluorescence with kind of unique capacities, always taking advantages of the good scaling up and the good cost factor when we talk about semiconductor technologies. In essence, the kind of experiment that we want to be able to monitor and to measure and to quantify in a convenient way would look a bit like that, right? The fluorescence signal coming from a sample of interest would be something that, first of all, needs to be excited. We shoot on a laser, an LED, whatever you want. Typically, we put it off afterwards, and then we get a signal that we want to quantify, which is the signal coming from our fluorophores. Of course, the excitation could be maintained all the time, and then we measure the fluorescence just using an optical filter to distinguish one or the other. But optical filters, you know that are costly. Having a good rejection factor is complicated. So let's think better about time multiplexing of the information. So first excitation, then measurement. So this is the approach we are following. And to measure the signal that we want, actually, we want two pieces of information. We want typically the intensity and also, if possible, the decay time of the signal we have, because this will tell us a bit more about the kind of fluorophore that is giving us the information. I'm thinking already in the possibility of having different light source fluorophore sources, which are combined and that we want to distinguish. There is not just intensity. What we want to know is specifically the decay time of the fluorescence that we have excited. To build up something like this, one could imagine, okay, I get a photodetector that is super fast and starts tracking all this light coming up and coming down, and then I get the signal, I analyze it, and that's it. This could be done, but of course, you know that these decay times are in the scale of nanoseconds or less, so it's kind of complicated imagining a fully analog approximation to all this measurement, the intensity and the decay time. Luckily, if we really think at what's going on in this experiment, this experiment that microscopically looks like this intensity profile of light coming from the sample, actually, we'll know that something going on that looks like this. Yeah, these are photons coming from different fluorophore elements. Let's assume one photon per fluorophore. This macroscopic shape, what tells us is, hey, you will be getting more photons in this range and less photons in this other range. That's the only information. But still, there are photons coming one after the other. So what we are really doing in this approach is, instead of thinking about measuring the curve with full accuracy, what we want to look into is counting photons. We know that photons will be coming, so we will see when they come, and if we have all this information, we will put it together to reconstruct from a digital point of view the analog information that, by other means, could be maybe more difficult to implement, at least in a really compact setup, sort of say. Let's begin with the excitation source. What kind of options we have here? Of course, we have lasers. Of course, lasers are complicated. Of course, lasers could be potentially integrated, but that's not the name of the game that we are playing. The alternative to lasers are LEDs. Of course, LEDs, their spectrum emission is a bit broader, a bit, not so perfect in terms of a spectroscopic application, but still quite affordable, accessible, and sufficient for many cases. Of course, we went in the direction of LEDs. When talking about LEDs, we have different options. We have the options of inorganic LEDs, which is ours. Nitrides are inorganic LEDs. Of course, we could also use OLEDs, which have a set of advantages and a set of disadvantages. Typically, in the long run operation, intensity of brightness, and so on. That's one thing. Typically, what we can find in either solution is things in the form of displays. As I told you before, display is one thing, array is another thing. Displays means that these are arrays of emitters intended for human visualization. This is good. This is flooding the market, so they are super available. But if it's intended for human visualization, this means that the operation rate will be slow. Will be designed for the observation with the human eye, typically. Yeah, and the human eye is not at the nanosecond range. Yeah, so this directly put these straightforward solutions out of the question when we talk about this. So what we really need to use are micro-LED arrays. This work will be about this last option, using micro-LED arrays as excitation source for fluorescence measurements. Of course, in the past, many other little small systems have been developed, typically single-point measurements with lasers, with LEDs, with micro-LEDs as well, but still one at a time. What I'm showing you today will be what happens when you put together manifold micro-LEDs together in the shape of an array to make this kind of measurements, and why this has some advantages, to say the least. So coming back to micro-LED arrays, we have already talked a lot of them. I guess I already mentioned about the advantages and disadvantages. So an array of pixels designed at will to be fast, power efficient, bright, fully custom, and so on and so forth. And that's what we can do in our clean room. In essence, what we do is we take a piece of nitride semiconductor, we grow on top of it the layers with the doping appropriate to make LEDs, so that this semiconductor emit lights. This is completely planar and two-dimensional, fully isotropic. And then we begin processing. We put some insulator on top so that we can connect things without short-circuiting some other things, and we start drilling holes to reach the different layers of the semiconductor, putting metals to make connections, and that's it. Yeah? Out of this 2D with a sort of 3D profiling, we can get a structure which actually looks like that. This has a slight three-dimensional profile that gives us access to different pixels of the LEDs that we can switch on and off in essence that way. That's what a micro LED array is. Next question is, how do you switch it on? Yeah, you have a plethora of different pixels. You need to switch them on more or less at will to make the patterns that are interesting for your application. One naive approximation would be what it's called direct addressing. So building a driver for each one of the pixels. This is possible and this works. That's fine, but you can imagine what's the problem here. If you need to have a driver for each one of the pixels, and you imagine that you have them in a grid arrangement, the number of drivers you need scales with the square of the number of pixels you have. So in lateral size, I mean. So this is kind of complicated to make it bigger. It's complicated to make it bigger, but it's super flexible. So you have full control of what's going on here. But the price is that the routing and the interconnect is kind of complicated, and this is typically used for really small arrays. Another option, which is way better, is what it's called matrix addressing. So this means that you have control of rows and columns, and then you switch on and off in the crossing points. This is typically the way to go, because you can replicate this structure more or less at will, so you can make really big arrays, because the number of drivers only scales linearly, sort of saying that. Better than that, it's hard to imagine anything, right? So that's in essence the two options we have. Matrix addressing is good for good scaling up and making large regular structures. Direct addressing is good for a few pixels, maybe even smaller pixels can be processed this way if you want small light sources. But of course, this does not scale well because you need to route each one of them. That's a bit the alternatives we have. We choose to work in this work with matrix addressing. So in essence, what we built was a driver for the columns, for the rows, sorry, a driver for the columns, and then connecting it with a gallium nitride LED matrix, LED array. So here you have an example of hybrid integration. Yeah, in essence, we have the driver made of silicon, of CMOS. This is super fast, super complex, digital signals. You can program it, connect it with a USB, whatever you want. This is silicon. But then you see the kind of complexity that you can reach with nitrides. In essence, diodes connected in a grid shape. So super many complex networks of transistors are still far away from the possibility of some nitride technologies. That in essence how the system looks like from the point of view of the logic. In reality, for the hybrid integration, what we use are nanowires. Actually, this is an interesting process that we grow copper nanowires in the metal contacts of the nitride and in the metal contacts of the silicon chip. These nanowires are used like Velcro, if you want to put it this way. So you align the chip, you press, and you get the connection. Yeah, this is just an effective way of making this hybrid interconnect method. You may say, why this fancy nanowire stuff with this hybrid appearance? Well, the question is that all these technologies, both of them, have very different topographic profiles. So you need to accommodate very high difference in height in the two devices. So the typical balls that you use in electronics here may not work well. Yeah, so that's why we need this flexibility that the Velcro nanowires, sort of saying, are giving us, in essence. Just for benchmarking about the micro LED array we are using, here in essence is quite unique. It's the one intended for fluorescence measurement. It's not a display. The main parameter you may look at is in here. Pointer is gone. Here, 500 megahertz. Yeah, the thing is that we can make images at a super high frame rate, which is not possible in a conventional display because nobody has such a fast eye, right? That's the bottom line reason. Also, the pixel size is relatively small, 100 microns for pitch, and it's also capable of pushing quite high currents. These 20 milliamps for these small pixel sizes are quite shiny LEDs, which are interesting for fluorescence excitation, as you know. So that was about the excitation source, the micro LED array that we were talking about. The next question is, how do we manage to measure these two things? Yeah, intensity and decay time. As I said, we will take advantage of the fact that actually intensity and decay time are macroscopic evidences of the fact that photons will be coming one at a time at different rates, at a higher rate in the peak moment, and as time goes by, less and less photons will be coming and so on. So you can imagine that the trick here is taking advantage that this is some kind of ergodic process. The idea is that you repeat the experiment many times and you keep on accumulating information until your digitally fully yes, no data turns into something that is a bit smooth. It looks a bit more analog, as we will see now. As for the detectors, I mentioned before that we have competences in SPATs, so single photon avalanche diodes, yes, which are a kind of photodetector which is designed not to quantify light, but to detect the arrival of a photon, to detect the arrival of even one single photon. The big difference of a SPAT or a single photon detector compared to a conventional CMOS sensor is that they allow for detecting the arrival of one photon, but they are unable, in the typical configuration of avalanche, of distinguishing if it's 1, 2, 3, or many photons. Yeah? They just say, hey, there is light coming in now, period. Why is it possible? Well, the thing is that in conventional photodetectors, what we use is the arrival of a photon. When it reaches the semiconductor material, it produces an electron, and this is a source of current that we can measure. Yeah? So the more photons that are coming, the more electrons we will have, so the higher will be the current signal that we will be able potentially to measure. That's the working principle. Does it mean that in this configuration we can measure one single photon? Well, it's very likely that not, right? Because one photon means one electron. If we think in room temperature, cosmic radiation, many sources of possible electrons floating around, distinguishing one single electron is kind of unlikely. Yeah. So this is distinguishing here one single photon is not possible normally. Instead, in an avalanche diode, what we do is the following. So we have the photon coming in, it produces one electron, but it's designed in a way that this electron hits many others and produce a shower of many other electrons. Yeah. How many? Hard to say, but many. Yeah? So any simple electronics can be able to see this shower of electrons crossing the device. Yeah? So we lose the ability to quantify the photons, but we gain the ability of detecting at least one single one with quite simple electronics. Of course, these are one-shot showmans. So it's arrives a photon, you get the signal, period. I've done my job. Can we use it for quantifying? Yes, of course, by repetition. We have the chance of repeating the experiment and counting how many photons individually are arriving per unit time of a big unit time, of a slower unit time. You can make a guess. This many single photons arrive per second, sort of saying. Yeah? So this can be quantitative, but at the price of repeating. That's what an SPAT is. Of course, the SPAT has problems. If there is a cosmic ray coming in, you will get one signal, but possibly it's just 1 over a million. So this is just a source of noise. Of course, you will have electrons produced by spurious signals like thermal excitation. That's true. But again, at much lower rate than the potential light of source of light that you would be using. It's evident then that the SPAT will work better at lower temperature. But that's something we should live with. Another interesting thing we can do, and that's quite unique in the technology we have, is that we do not have just one SPAT, but we have a SPAT camera. We have a SPAT array. Yeah, so it's not just one single detector in one place that we try to align and that's it, but we have an array of at least 60 times 60 pixels. So it's not intended to make imaging, but to distinguish different light sources. Another advantage of this configuration is that, for example, optical alignment is very simple. You don't need to bother about optical alignment. You put your big area of the SPAT array in front of your source, and you just use the SPAT that gets the higher signal. Simple as that. You don't need really to align. You can do it by software. And that's pretty handy. Because the SPATs have a disadvantage that typically their active area is relatively small. It's quite small because if we make bigger SPATs, the chances of having random avalanches just by noise will be much higher. So typically the SPATs are devices, this version has not been saved. Anyhow, not a big deal. I was just going to show you the fill factor. Yeah. So out of every 10 microns of size of pixel, we need 70 microns of silicon just to protect this pixel. Yeah, so the idea of fill factor means that not all the area of the camera is active. Only the central 10 microns are active at a rate of every 70 microns. That's some information just to know as a user of this kind of thing. So we have a gadget that can tell us that a photon has arrived. And we know that this gadget we'll have to use it many times to count how many photons are arriving per unit time. The next question is, when are these photons arriving? We'll have a signal that will come after switching off the LED. At some point, plop, a photon arrived, and then we repeat the experiment. Yeah, the idea here is trying to figure out if we can measure when each one of the photons is arriving. And this is what the technique of time-correlated single photon counting is doing. Yeah, in essence, is finding out some kind of electronics capable of counting these photons, but not just counting them, but assigning them to a time bin, yeah, to a time period after the LED was switched off. Yeah, so by counting how many photons are arriving in each one of these bins, we can reconstruct digitally this kind of profile of the arrival of photons, in this case, applied to fluorescence. The electronics we developed do whatever, but in essence, what you need is something that counts time, that assigns the time to the photon that has arrived, and storing it into a memory. We can think it very complicated, but in essence, it looks like a domino system. Yeah. So when the LED is off, we kick the first piece of the domino, they start following, and when a photon arrives, it blocks the falling of the domino. So we count how many pieces have fallen. This means these many nanoseconds. So you have arrived at this bin of time. And then we put everything vertical again, and we repeat again. We do all this with electronics, but in essence, it's the same idea, with wires and signals. So once these two things are done, I hope I've sort of convinced you that out of these experiments and all the photons arriving, we should be able to produce something like this. This rate of photons arrived at each one of the information bins, so we really have information about the intensity, either here or just integrating everything, and we can also figure out the decay time of this fluorescence, so the other source of information that we needed. Since we have an array, we have spatial distribution, so maybe potentially we can have different places where we could be running these experiments in parallel, so measuring different sites or different areas of our biological structure, I don't know, yeah, both on the excitation or on the detector side, because we have a two-dimensional arrangement in the excitation and in the detection. So we can play with these two different things, acquiring lots of beautiful bell-shaped curves related to the decay of fluorophores taking place in different places, different samples. We will see some examples now. The setup in the end looks something like this. Yeah, so we have the micro-LED array. In this case, in this experiment, we use 32 times 32 pixels with 50 microns pixel size. It's controlled with a CMOS driver integrated in a hybrid way that has this fast switching circuitry. The SPAD camera in this case is 16 times 60, is placed in front, and then the sample we used was a micromesh grid with 250 micrometers wells with two quantum dot fluorophores marked with something that just shine at two wavelengths which are of interest. Yeah? So this is how far this technology has been validated and tested. We are certainly looking forward to application cases. So if there is somebody that finds an experiment for this with some much more, let's say, less demonstration and more applied use case, we are super happy to put it into practice. But today I will be talking just about the result from the quantum dots. The first thing we had to do was calibrating the system, which in essence means switching on the LEDs across the whole array, detecting it with the whole array of detectors, and seeing if everything is balanced or not. The answer is, of course, it is not, because these are optical systems with losses and so on, but this is something that can be normalized, and when everything is normalized, you can have your correction factors to have more or less the same signal from all the pixels. Typically, we manage to get homogeneities across the two arrays of better than 5%. The next thing, which is critical in this use case, is how good are you at switching off the LED? Yeah, because all the party is based on time multiplexing. So you need to switch off the LED to keep on looking at the light that does not come from the LED, but it comes from the fluorophore. Yeah. So this is really challenging, but that's quite a good number. Our LED system in these experiments was switched off in less than 3 nanoseconds, which is pretty fast in this sense. This also means that decay times longer than 3 nanoseconds are hard to detect with this kind of system. If the question is, can this thing be faster? The answer is potentially yes. And the reason is that the main limiting factor for this decay with this time of 3 nanoseconds is the capacitance of the LEDs. So potentially smaller LEDs with smaller capacitance to the area could be faster. The electronics are faster than that. The limiting factor, which would be some intrinsic semiconductor processes, would be in the range of 1 nanosecond. Going below that, I think it's science fiction, but 3 nanoseconds is something that could work. We put it to work. We switch on our LED array. We started acquiring millions of countings of photons from all the possible pixels. We build up a fake color image of the signals that we are collecting. And in this experiment, we had two fluorophores, one located here and another here, so we can see them. And if we start playing with the concentrations of the two fluorophores, we see that effectively the counts scale up properly with the concentration of the fluorophore. So that's what we want. We can use the amount of light directly as a measure of the amount of target fluorophore that we have there. And both of them shine at different intensity as expected, and they can be especially localized at the resolution of the micro LED pixels at least. About the decay time, the kind of histograms that I was showing before actually in reality look more like that. So this is the LED switching off time, and then this exponential decay that if we draw it in a semi-log scale, it looks like a straight line that we can fit, and we can actually measure the decay time or the relaxation time of the fluorescence process and quantify it. That's the most important part. We can quantify it and reproduce what the literature or the datasheet tell us that is the decay time of these two fluorophores. We can make good histograms, so one potentially can distinguish different origins in different pixels. So that's kind of experiments that are possible to do. And more interestingly, we can distinguish mixtures of fluorophores in the same sample and in the same spot. One could fit the exponential loss to the decay times of that, and using the amplitude of the two exponential to see if the mixture is really the one that we were expecting to have. So potentially, without the need of filters, one can even distinguish different fluorophores if the decay times are different enough. That's of course something that shows that works, and that's quite interesting. And that will be it, right? Yeah. Time is fine. Yeah, that's in essence what our system can do. It's just an example of the many technologies we can put together. As I said, looking forward for applications to these kind of things, to imagine new experiments, to imagine new solutions is what we like to do. That's what I had for you today. Looking forward to questions.
Thank you for the talk. Are there questions or comments? So you can detect the photons. Can you also then measure them? Can you measure some polarization or so? I'm just thinking about quantum communication. So if you detect them, can you do something with them?
A polarization filter could be added here. Yeah. Yes.
Possible.
That's possible, yes.
Do you think about this to use them for quantum communication?
There is a working group in NTC thinking about it in the Network Technology Center. There is a group considering the questions of quantum communications. Yes, that's a possibility. A specific thought. I guess that you have specific thoughts on that then, right? Good.
And yeah, perhaps to molecular communication, you are expert in sensing.
Yeah.
Can you think about how to sense molecules in some circulating systems like you saw in the demonstrator or test beds we saw here in the morning? Do you think about also to do something there?
Yes. I don't know if we will find the slide, but if you remember the one about the distributed microscopes, the whole topic of this, the whole interest of this technology is putting it around capillaries, structure, fluids, so things moving around. The idea is we use it, for example, not in this field, but just to show you that sort of similar things could be done. We use it for particulate matter measurement in air, so pollutants in air, PM. Yeah. So we collect air from the ambience, we pass it through a capillary, we take pictures, and out of each pictures we count how many particles, how do they look like. We try to get the spectral signatures of them. For example, distinguishing pollen from the leftovers of the brakes or the tires of a car is important in terms of contamination, right? So this can be done spectroscopically out of these images. Is in gas phase, moving into liquid phase. That's the kind of things that we can do. Yeah, with the right partner, of course.
Okay, thank you.
Thank you. That's extremely interesting. So one quick question. Maybe I missed that, but what happens if the fluorophores they are on a surface that is not transparent?
Today we have a problem, but it's possible to set up this thing in reflection mode.
Yes.
Yeah.
Okay. I was thinking about that.
So the good thing of nitrides, it's not a good thing. It's just serendipitous. It happens that nitrides by themselves are transparent. So you can consider putting them on top of the SPAT detectors, and at least having at the same time the emission going forward, getting back reflection, and the detector behind. So all this concept could be flipped to one single side.
Okay, I see. Okay. Extremely interesting.
Good.
Yeah, thank you.
Just a very quick one. You had these bins.
Yeah.
What is the time duration?
I
of one
think
bin?
it's about 20 something picoseconds.
Again,
20 something picoseconds.
picoseconds.
Yeah.
Okay. I was thinking about an application for communication
Okay.
without quantum first.
Okay.
And then of course it would be interesting because that somehow would be corresponding to the bandwidth
Yeah.
of the signals that you can detect.
Exactly.
So the smaller the bin, the better.
And I understand. Yeah. The first, actually, we can see it a bit here. Yeah, it's we will have the nanoseconds here. It's a bit too thick, the line to distinguish. Yeah, but let's say that this is already filtered, so it's faster than a nanosecond for sure. Yeah.
And as a follow-up from this discussion, would it be possible to picture a cross-section of an optical fiber?
With a SPAT camera, yes.
Yeah, because that would open up, I mean, even more spectrum, I think.
Mhm.
Okay.
This is, I mean, to put in the part of the photon counting, there are some trade-offs you need to make in the fill factor, which is what could be critical here. But I don't know what's the kind of problem, but you've seen that the spacings in the range of tens of microns for the sampling across the fiber, this could be possible. Yeah?
So you could have a picture practically
Yeah.
of not only one photodetector.
If it has some circular symmetry, one could even imagine not a 2D camera, but a one-axis camera to get a cross section, and then you could get even more dense SPAT pitch between the pixels. For example, I'm thinking out loud. I don't know, but there are possibilities that can be done.
Okay, thank you. Just putting it out there.
It makes there are some people happy around, so I'm happy about it. Then let's talk about it anytime.
So what I didn't get, so I'm not a microchip person.
Yeah.
How are these devices tuned, or basically what am I measuring? So, for example, let's say I want to detect or measure the concentration or intensity of a certain protein, and I know the excitation wavelength, and I know the wavelength which is coming back. Is this, how do they have these arrays to be modified or tuned to that, or are they adaptable in some sense?
Okay. One thing is defining the excitation wavelength. For this is it.
Yeah, let's say we know that. So
We know it. We know it, but then this means that we need to pick up the composition of nitride which fits that wavelength. Yeah, that's a matter of picking the right semiconductor and fabricating the device ad hoc for this excitation. Yeah, that's one part of the story. For the detector side, it's not so critical because these SPATs are quite broad spectrum detectors, and that's how it works. They reach quite into the visible and mostly in the infrared. They are silicon. That's what they are. Yeah. So the spectral selectivity, there is not much there. Spectral selectivity is in the excitation side. That's it. I answer, right? You choose the material, we fabricate it for this experiment. What else do you want to know? Maybe the quantitative aspect. Yeah. The quantitative aspect only goes through the comparison with a reference sample. So out of this, you get for a given excitation rate a number of counts. So this many photons per unit time at that time.
Yeah, that's okay because
that's calibration.
Numbers don't matter. It's
okay.
Like just relative. Okay, and how expensive is one of these sensors? So just
yeah.
Maybe I can also ask, where can I buy it? I would try it out there.
I mean, it's not crazy expensive. The part of the silicon is I mean, we don't fabricate it, of course, we send it to foundries. And if the design is made, something like that, it would be just the cost of a multi-wafer project, which typically is in the range of 15,000 euros sort of thing, to share in between many components. So eventually, I don't know, some thousand, or this range or less per unit, depending on the amount of units you need and so on. So, but it's more, it's more a private conversation about collaborating than really costs. So I would rather say at this scale, because Because if you have to design it, of course, you need to put on top the price of the people. Yeah.
Only a small question. So you had these parallel branches where you did the counting of the bins.
Yeah.
Of course, they have to be synchronized.
Yeah.
You know, is this difficult to achieve? Is this part of the you mentioned this calibration? Is this also part of the calibration process that you have time synchronization over these parallel strings?
Yeah, I mean, if I get the question right, I mean, just imagine how the silicon part works, the CMOS part works. It contains both the camera and the driver of the LEDs. So it's the same CMOS circuit, the one that is in charge of switching on the LED and switching it off as fast as it can, and it has the clock. Yeah. So once the LED is off, all the time counter begins in synchronization within the CMOS chip, and there really the synchronization is in the range of picoseconds. Better. That's not an issue, and then time counting goes from there. So keeping in sync the LED with the detection it takes place in the same chip. So the clock is common. It's fully synchronous. This one, I guess, right? No, actually, what it tried to represent is that one can collect many different spectra coming from different places, eventually from different samples, and for different experimental conditions. Yeah, and the binning is the same for all of them because the time counting electronic is common for all of them. Yeah. Mm.
Okay, then thank you again, and thank all speakers of today.